Hello all. So the paper that we'll be reviewing today is completing the knowledge graph. Knowledge graph completion with knowledge graph completion by it's an IEEE paper by Ying, Shen et al. So let me start ahead. So basically, a knowledge graph uh, is a collection of entities and relations which provides relationships between entities. An entity can be any uh, anything, object, place, or a person. So these are a few of publicly available knowledge graphs: DBpedia, WordNet, Freebase, Wikidata, and Yago. So what we are trying to do here is to identify what are the missing components in knowledge graph. And usually when you're trying to find an answer in knowledge graph, the path from the source to the target can be very noisy. It can get very noisy. As an example, you can see this graph where Despicable Me is a movie produced by Chris Melodendry, and Elsie Fisher is the one who voiced Agnes, which is a character in Despicable Me. There are if you ask this question, what American cartoons is the producer of Despicable Me, you can there's a direct path to Chris Melodendry, and that does not have any noise. When you ask the other question, who first voiced Agnes on Despicable Me, it has a very long path which has to be figured out from multiple relations. So it goes like Agnes Grew is the character in Despicable Me, and Despicable Me was in 2010, and Despicable Me 2 was in 2013, and Elsie Fisher was the actor who voiced Agnes in Despicable Me in 2010. So this adds noise kind of to the knowledge graph to figure out the actual relation between two entities. Instead of adding this, going through multiple hops, we could directly add another relation from Despicable Me to Elsie Fisher, saying that first voice actor. So that is the problem that the authors have been trying to tackle in this paper. There are a few problems for this. If you see the multiple hops, along with multiple hops, there may be knowledge incompleteness, as in what if nobody had given added an information that corresponds to the voice, the actor who voiced so and so character in a movie. So that is where we do not have a knowledge regarding the question. For suppose, and Wikipedia, as we know right now, the growth of Wikipedia has been slowing down. It has not been growing at the same pace that it used to in the beginning, and maybe because the people ran out of the people ran out of the things that people already know about, or only new things or cliche things are left out to be added to Wikipedia, and the people who know about them are not as free to update Wikipedia as such. So there are multiple reasons, but still the Wikipedia has a lot of missing data, and it also is not growing as fast as we imagine it is growing. So the other problem is also representational sparseness, as in when you can convert all the data from text to or partially structured data, your, as you might have seen, Wikipedia page, each Wikipedia page has a kind of knowledge graph or a knowledge component uh, for each concept. Let's say you ask about computer science, it will give So for every page you can see a box here, or maybe let's say I'll use Obama. um let's say Barack Obama. So you can see this structured information as a card here. So this is a little structure representation format, but this does not cover everything that is in this text format. So that's where we get representational sparseness. And few of the studies that have tackled this problem have come up, I mean they did not consider the type information of the entities as such. They have ignored the type information, like even when you say that here in the example knowledge graph, if you see, um, Agnes Grew is has the type of person, also it has a type of actor, also cartoon character. So these types, entity types, give more insights about what can be inferred from an entity, or the path which has to be taken. So if we ignore that, we are losing on some valuable data. And also there are interaction between different semantic representations, as in, if you if you see this, if you take the English words as such, we may not be able to see the interaction between them, but to if you if you consider them as separate entities, you are not going to get the whole idea about the path. But if you also take into consideration the interaction between different entities, then sorry, different relations, or the relations in the path and entities, then it gives more insight about why to follow so and so path. So that is something that these authors have focused really upon. And also there is a downside uh, uh, for considering the type information, because adding more information may not be very well positive, or give positive results, or may not be helpful all the time. There may be noise that also gets incorporated along with all the good things. And so what if the next problem is like factor and conflict. So it talks about what if the representation itself is wrong. Let's say somebody gave wrong information, and we are going to think that it is right, and going ahead and getting the answer that's not going to be correct. There may be few paths like that which affect our decision on which path to consider. So regarding these problems, let's see how these have been addressed in this paper. And yeah, coming to completion methods, uh, because we have the problem of representational sparseness and knowledge incompleteness, we can there are a few methods that have been proposed or explored before by different authors. One is relation extraction. If we can find a direct relation by extracting it from the source, we can use that. And path reasoning is a very famous algorithm that has been worked upon by different authors. So we can rank the path using proximity, and try to identify which is better. We can use Bayesian clustering, energy based models, matrix factorization, and recently few methods that got a lot of traction are translation based methods like trans E, trans H, and trans R. So what they do is they represent as a they represent the relation as a translation between two. So they represent the relations as a translation between one entity and the source entity and the target entity, and that captures semantic information between the source and target entities. And we also have shared memory and controller approach, score pooling methods like top k, log sum exponential, I guess, or averaging. Tensor factorization is same as like matrix factorization. And multiple neural networks have also been explored to identify the most dominant paths. And the multiple neural networks and mining observable patterns in the graph. So observable patterns in the graph is also another approach that has become very popular. And attentive path combination is also helped. So attentive path combination is the closest kind of approach that the authors of this paper have followed. But the downside for attentive path combination and taking an average score is that it does not know which path to weigh more. There is no weightage difference in an average attention. So in basically as far as attention goes, you need to rank something higher and rank something else lower. But if you are taking an average, you're just considering the whole path to have the average value, and that is not going to help much. The place where this paper shines a lot is they have, instead of considering the average score for the attention for the path, they have considered individual scores for each entity type and relation, and then they are providing that as an attention vector and attention matrix. That is the main key difference or the unique selling point for this paper. So these are the most relevant works. Anerwas et al. Has created a deep learning model from natural language text based on attention, and Canavico et al. Has used information extraction and built two systems called NEL and Knowledge Vault on the same idea. Neural attention modeling with multiple paths has also been explored by Das et al. So it also uses neural networks, and link prediction problem with variational inference has been explored by Chen et al. So link prediction is basically trying to identify out of all the possible paths which path is the most closest or the most predominant for the question between two entities. So the approach they have taken is type-aware attentive path reasoning. So as a part of their approach, they have created a knowledge enhanced attentive path reasoning model. Like we discussed, we need to reason about the path, like why this path is the best for identifying the answer to the particular question. And the first effort to study this is like the first time anyone has tried to study entity type discrimination in the path reasoning for knowledge graph completion. So basically what they're trying to say is that nobody has tried to consider entity type. Everyone has considered like entities and average scores, but type information has not been used much except for the translation papers like trans E, transition, transfer. So these guys also have used trans E. We'll go deeper about the techniques in the methodology. So let's look at methodology. If you look at the methodology, there are let me show the whole approach first. So this is how the methodology, the architecture for their approach looks like. The components, if you look at, you will be able to see a structural knowledge learning, textual knowledge learning, type information learning, and the combining them together to identify the path. That So let's try to identify what is structural knowledge learning. So basically structural knowledge learning means identifying a structure, giving structure to entities and relations. You are converting you're trying to identify entities and relations and embed them into their structural embeddings. So it's kind of trans E takes care of a pre-trained trans E model is applied on entities and relations with a subset of free ways to identify structural embeddings. It can be thought of as a word vector for each of the entities and relations. So now coming to textual knowledge learning, the next part, we are going to represent words and sequences. The words are represented using glove embeddings, pretend glove embeddings, and sequences are trained using bidirectional STM. So the input word vectors are fed into both forward and backward paths of by LSTM, and then the output has been stored as entity embeddings. So that is for textual knowledge learning. And coming to type information learning, so basically textual knowledge learning only consists of entity embeddings, whereas structural knowledge is applied both for entity and relation embeddings. Coming to type information, which is the core part of this paper, for the type information learning we have type word embeddings and type sequence embeddings. So here we are going to take the type of entity and the type of relation, not the entity and relation themselves, but the types of but their respective types, and we are going to pass them through BiLSTM and get the embedded representation, and then we will be passing them to the next layer of attention, which is word level attention, and which is that attention is calculated dynamically based upon the words themselves, the types themselves, and which in turn connects to a linear layer. um, so here you can see that the relation type is being added as a uh, added along with a learnable parameter to the entity type embedding. So uh, relation type embeddings also play a role in creating the entity type embeddings, and that's how we can get semantic representation of the path and score it based upon the attention values. So the relation type embedding here is basically a sequence representation of relation type, and entity type embedding is a sequence representation of entity type, but only that they have the attention added now based upon the type. So coming to the overall architecture, combining the three modules that we have discussed till now, you can see that the relation representation, let me try to pick a, the relation representation is concatenated from the type information, the structural knowledge learning. So here what you can see is that entities and relations processed by trans E are in the same vector space. So because we are using trans E to encode the entities and relations, both the structural representation of relations and entities and the types of relation entities are going to be combined together to identify the relation representation from trans E and the BiLSTM attention. So whereas the entity representation is figured out by concatenating the entity type embeddings, the entity textual embeddings, and the entity structural embeddings. So because we have attention provided in entity type embeddings, so we are going to make use of that information here while feeding that to GRU GRU layer, and which again imposes attention to identify the correct relation vector. So this is the key here, the word level attention and the attention layer for figuring out the relation. So these two attentions are what make this paper stand out from the crowd and help a lot in identifying the correct relation for the new path. So that coming to the data set, it is a subset of the Freebase 2 with almost 1.5 million entities and 27,000 relationships. Out of those, for test, they have taken 46 relationships and 2 million entity pairs. Uh, so they have 23,000 intermediate relations and 199 million paths in total. Average path length is 4.7 and maximum path length is 7, which is like a good amount of length. So these are the results that I have compared against existing you know existing models, and as you can see that their model performs really good with path attention. So they also have if you see, like, they have attention grew, attention model plus type. These are without type information. So TAPR is the only one which makes use of type information. So the type effect, they have done an ablation study with and without type attention. So the dotted line you can see here is without type, the same TAPR model but without type. When the and the long dots are like without type attention. They have added type information, but they did not add attention yet. But once they add attention, you can see that they have very better results compared to without type or type attention. So let's look at a case study before we end our talk. If you see the case study here, I wanted to give like what is the exact output from this paper. Okay, so if you take a look at this example, in Suffolk County, Fire Island suffered the most damage according to Jean Claude Glean, the villager of nearly 19 years old. So here, what you can see is that Jean Claude Glean is the villager of Suffolk County. So, but the representation of this text in knowledge graph looks something like this, whereas the there is no direct link. This is the link that we are predicting, the location slash resident. The existing path is this location contains fire island, which is the mm, which is connected to John Cloud by person living place or person workplace and person birth place of birth. So out of these three relations, we can see that living place makes most sense, and this has been identified given the highest score by this TAPR model. So the graph that you're able to see here is the average of the number of entity types less than 8 for 20 relations, and the performance of TAPR is pretty good for um, short average number of entity types. And if we consider more entity types like longer relations, we see that the performance degrades by almost half. So the other use case that they have covered is link prediction, which is basically if you take a look at this, like this example, in infectious shock and emergency department are uh, connected by medical department relation. There are two paths. One is infectious shock is a disease alias for septic shock, and septic shock has medical department, emergency department. So this has been identified as the most relevant path than infectious shock is a complication for disseminated intravascular coagulation, and that is a complication for abdominal pain, and that is a complication for electrolytic disturbance, and electrolytic disturbance is a, as you can see, there is a lot of noise here. You cannot identify what is the direct relation between infectious shock and emergency department, but for the first part you can easily identify that septic shock, the medical department corresponding to septic shock is emergency department. And also if you see, beryllium poisoning is responsible for pulmonary edema. You can see that the first path, beryllium poisoning is a complication. Pneumonia is caused by beryllium poisoning, and pneumonia has a lower respiratory infection alias, and that causes pulmonary edema. That is a syndrome of pulmonary edema is syndrome of lower respiratory infections. So this is more direct path than the other path, which uh, goes through urinary calcium and hyperkalemic nephropathy and that to urema and urema 2. So this is much longer and noise prone. So this model is really good at identifying the crisp paths, is what they say. So, and coming to the running times of training, it stands somewhere in the middle of PRCTA and attention model plus types. And I think that that concludes my talk on this paper. So as a key takeaway, I think they did a very good job in identifying using attention mechanism and type information to identify the relation, the paths, and coming up with uh, you know precise answers to a few questions. But they did not, what they missed is they did not say anything about how they are going to tackle missing information or incorrect information, even though they uh, you know say that these are the problems. They did not say anything about how they can be tackled, or they did not have any study on that. And uh, 78% I think uh, is not so good enough for you know uh, some to identify answers, but still it's good improvement on previous you know previous work, previous study. And yeah, and the process itself is good, but the relation, the results, I think need to be improved, because they did only on freebase. I'm not sure if they also had included more data, they might have got better results, because especially with text models, more data means better results always. So I think those are a few things that can be improved in this paper. Yeah, thank you so much for your time.